Electricity, two charge problems. Questions to ponder. What is electric force and Coulomb's constant? What are the units for charge, electric field strength, and potential? How do you calculate electric force, field, and potential with two charges? And what are equipotential lines? Let's do a quick review of force, electric fields, and potential. If you recall, electric force comes from Coulomb's law here, that the electric constant times each of these charges that are interacting divided by the distance between them squared here. And notice if the charges are like charges, they're going to be repelling. If they're opposite charges, they're going to be attracting. And of course, this force is equal and opposite. Notice if you do know the electric field strength, then you can find the electric force simply by multiplying the electric field strength times the charge of concern. Next, to find the electric field, this is our reference charge, and this is our test charge, little q. The electric field out here at a distance r away from this charge of concern is equal to the electric constant times this charge and divided by the distance out to where we're concerned with squared. Notice if the charge is positive, the electric field vector goes outward. If the charge is negative, the electric field vector goes inward. And of course, the electric field can also be calculated if you know the electric force and divide by the amount of the test charge. Finally, electric potential out here. Electric potential is equal to the electric constant times the charge of concern and divided by the distance that you're away from the charge of concern here. And electric potential can be calculated also if you know the electric field strength by multiplying by the distance that you're out and away. Notice also that potential is a scalar quantity. It is not a vector. Before we dive into our problem here, let's go ahead and take a look at some units and our constant that we need to know. Recall that force doesn't matter what the force is created by. In this case, electrical force. Force is measured in newtons. Electric field strength is how much force there is per charge, and so it's newtons per coulomb. And potential is measured in volts. We'll come back and take a look at a volt in a minute. Before we do, let's look at this important constant here, our electrical constant or Coulomb's law constant. It is 9 times 10 to the 9th newtons meters squared over coulomb squared. That is 9 billion newtons meters squared over coulomb squared. This is such a huge number for two reasons. One, the electric force is a very, very, very strong force. And the other reason is a coulomb is a huge number. So for those reasons, K is very, very large. A coulomb is 6.24 times 10 to the 18th electrical charges. So that's 6, 2, 4, and 16 zeros after it. So again, that's a huge, huge amount of charge. Now let's look at the volt. To understand a volt, electrical potential energy is equal to charge times the electrical potential. Therefore, electrical potential is how much electrical potential energy there is per charge. So 1 joule per coulomb, again that's a huge number, coulomb's a huge number, 1 joule per coulomb is equal to 1 volt of electrical potential. And also we need to know a little bit about micro and nano. Because a coulomb is such a big amount of charge, we usually don't talk about coulombs as much as we talk about microcoulombs and nanocoulombs. So a micro, if you can recall, is 1 millionth, or 1 times 10 to the negative 6 of something. In our case, charge. So 1 microcoulomb is 1 times 10 to the negative 6 coulombs. And just to equate that to charges, you can still see that 1 microcoulomb is an awful lot of charge. A nano, which is 1/1000th, 1 times 10 to the negative 9 of something. 1 nanocoulomb is 1 times 10 to the negative 9 coulombs. And still you can see that even a nanocoulomb is 6.24 billion charges. Before we do this problem, I think we need to get charged up. And do the Harlem Shake. Yeah, I don't know if we can get that excited about doing one of these problems, but we'll try to have fun with it. All right, we have two charges here. We have a 4 microcoulomb charge right here at point A, and we have a negative 2 microcoulomb charge here at point B, and they're 5 centimeters apart. And our job is going to be to find the electric force between those charges, the electric field strength, and also the electric potential at point B. So we're going to start off by finding the forces here. Why don't you give it a try? And also you want to draw the vectors at point B showing the electric force and the electric field. Why don't you give this a shot, and after you're done giving it a try yourself, come on back and see how you did. So, how did you do? Let's check it out here. Remember the electric force. We were going to go right to Coulomb's law here, and we have our electric constant times each of the charges here. Both of them are in microcoulombs, so that's 10 to the negative 6 here. And then the distance between them is 5 centimeters, so we have to remember to convert from 5 centimeters to meters. And then we're going to have to square that as well. So once we get done plugging all this in, we should have an answer of negative 28.8 newtons because of the negative charge here. So the negative simply means the force is in the opposite direction to the electric field. And since these charges are opposites, the force is going to be going toward, this negative force is going to be going toward this positive charge here. That would be our force vector. The electric field strength, right here, the electric field, since this is a positive charge that we're referring to, the electric field vector would be pointing outward, and the electric field would be kq over r squared, and this would be the charge over here that we are plugging in. And after we do that, we get 1.44 times 10 to the 7th newtons per coulomb. Remember, electric field strengths, you should be getting large numbers, where electric forces, you'll be getting kind of ordinary size forces there. Since we knew the electric force already, the easier way to do this problem is actually to take that electric force and divide by the charge here, and we should still get the same answer. Notice the negatives will cancel here. And we could work backwards if we knew the electric field strength. This is just showing that you could work backwards to get back the force using this easier equation. Force is equal to electric field strength times the charge. Finally, our potential. This is the standard way to find the potential down here, is kq over r, and we get 7.2 times 10 to the 5th volts. So that's a very, very high voltage, as you can see here, high potential with that amount of charge so close here. Potential can also be found by taking the electric field strength and multiplying by the distance of concern there too. So that's the problem. Hopefully we're successful. Next, let's take a look at equipotential lines. Equipotential lines are lines like these two red lines here that are equal in potential all the way around here. So if we have a positive charge, the electric field lines would be emanating outward here and pointing radially outward. The equipotential line would be where the voltage would be the same everywhere around here. So let's say that this is 10 volts here, then it'd be 10 volts here and 10 volts here, where the voltage would be more closer and less further away. Notice that at this point where it crosses the electric field line, it's perpendicular to the electric field line and or tangent to it there, and that's true all the way around. So that would be an equipotential line at one potential. This would be another equipotential line at at less potential out here. So if that were equal distance out here and this were 10 volts, this would be only 5 volts out here as you got further away from the charge. Notice what happens here when we have opposite charges, and opposite charges attract, so we'd get these electric field lines here of attraction, and they'd go out and around and everything like this. If we could see here, the equipotential lines are these circular or oval shaped kind of lines here, and then when you get right between these two opposite charges, you would have an equipotential line. It would be actually straight, perfectly straight up and down right here. So anywhere along this line, the potential would be the same everywhere. That's true around this line too. When you have like charges, and we get this repelling here, in this case the field lines are going inward, the equipotential lines, which are perpendicular to those field lines, make these kind of unique curves. They're easier to visualize if we pull them out here, and so you can kind of see the general structure of the equipotential lines if you had like charges repelling. Hey, let's go back to our FET simulator here, and let's check out these equipotential lines around a positive charge. I've got my equipotential meter here, or a plotter here, and I'll click on plot, and it'll make equipotential lines as I move away here and click, and you can see that they are circles around that charge if you have an individual charge. And let's clear that, and let's see what happens if we have opposite charges here. Let's have a positive over here, and we can put a negative right over here. And now I'm going to plot these equipotential lines and move over and plot and move. I'll start from inside here and plot. And again, these lines are where the potential would be equal all around that whole line. As we get closer here, notice that these kind of become a little oblong in the center. If I get dead center here, right in the middle, it should be pretty close to a straight line. Move over a pixel here, and pretty close to a straight line. So if you have opposite charges here, the equipotential line perfectly between them would be a straight line there. And finally, if we have two like charges, this is what the equipotential lines would end up looking like. So here we go, plot, plot. They would start to get pointed toward the center here, and then when you get right near the middle, they should crisscross, kind of make an infinity sign here, like that. Pretty good. And then as we get around here, they start to kind of broaden around the two, and then eventually at some point out here would make kind of like an ellipse. So those are equipotential lines. You should get on FET here and try it out yourself. It's kind of cool to play with. So if you want to simulate it yourself, go to FET, Charges and Fields, and check it out. So your questions to answer: what is the electric force and Coulomb's constant? What are the units for charge, electric field strength, and potential? How do you calculate electric force, field, and potential with two charges? And what are equipotential lines? And Scratch's parting thought: and hopefully you are striving for continuous improvement.